This lesson deals with comparator limitations. What we're going to take a look at is the data sheet of the LM139 comparator, and also compare this to the model and model performance that we get with SPICE. Just like an op-amp, a comparator has a voltage gain because it's really an uncompensated op-amp. If you look in the LM139 data sheet, you can see that in its column of numbers, there's a listing for the typical voltage gain of 200 volts per millivolt, which would mean 200,000. So the same as a 741 op-amp. Next, I want to take a look at the output sink current. And this really goes back to the schematic of the comparator. So if you look at the last page of the data sheet, it shows this picture, which is sort of an equivalent circuit of the comparator, replacing what are called current mirrors by just their effective current sources. So here you see this open collector transistor where we're going to hook up a resistor or maybe an LED or a motor to complete our circuit. We can figure out some things about the transistor by just looking at the data sheet. Now from that schematic, it says that the current feeding the base here is 100 microamps. So when the transistor is cut off, of course, no current goes in here, it all goes into this transistor. But when you saturate the transistor or make it go active, all that current will go in the base. So the largest base current that we can get is 100 microamps. Now in the data sheet, it says that the most current that you can sink in here, which you can take in, is 16 milliamps when the voltage across it's about when the voltage across is about 1.5 volts. So what that implies is that the beta of the transistor would be this current of 16 milliamps divided by the base current, about 160. So we get some idea what kind of properties this transistor has. For the most part, we're going to keep it saturated, but sometimes the transistor will go active because of the load that we hook up, especially if we put an inductive load on there. Before we go on to the next parameter, let's take a look at that data sheet for the last two that we just did. So this is page 2 of the LM139 data sheet. And here's the LM139. There's some other variations based on temperature performance, but let's just take a look at this column right here. So here is the voltage gain, and it's 200 volts per millivolt. And here's the output current sink, and it's 16 milliamps. Those are the numbers we used on the previous page. Let's go back to the notes here. The next parameter to take a look at is called the saturation voltage. And this, of course, is when that transistor on the previous page saturates. And in the data sheet, it lists here as 250 millivolts. And we can, again, take a look at that on the data sheet. It's on the next page, actually. Slide down one here. So here's the saturation voltage of 250 millivolts. So this to tell us what happens when we saturate the transistor. And so our output voltage is going to be our power supply negative plus the value of the saturation voltage. Most of the time we're going to be using a 0 volt power supply for the negative, and so it would just be the saturation voltage. So it's not really 0 volts, but about 1/4 volt. We'll kind of treat it as 0 just to make things easier, but it does have a value, and sometimes we need to consider that when we're looking at errors. Next thing to take a look at is what's called response time. Now the comparator is not internally compensated like the op-amp, so there is no slew rate. It simply switches as fast as it can. It's really limited by the transistor capacitance. So if we take a look at our transfer curve, again, so let's suppose that we have a 0 plus power supply. So we're going to saturate from roughly 0 volts to roughly the positive power supply as we pass through 0 volts for Vn. Okay, now suppose that Vn goes from a negative voltage to a positive voltage. What's going to happen? Well, the output's going to try to go high, but it's going to take some time for it to respond. Now suppose that we started out at minus 100 millivolts here, which is negative, more negative than the power supply, but as long as we're not more negative than one diode drop, we'll be okay. So the ICs are reverse biased diodes basically to build the substrate and the transistors on it. And so if we don't go more negative than the negative power supply than one diode drop, we'll be okay. So starting out, say, at minus 100 millivolts, suppose that we overshot 0 by 20 millivolts. What I've taken is a shot of the sketches on page 4 of the data sheet that shows what happens. There's a little bit of a time delay, and then there's eventually a rise time, and it goes to the output value of the saturation voltage, which is roughly the positive power supply. In this particular case, it was 20 millivolts of what's called overdrive. This is overdrive going from low to high on the input. But if you were to overshoot by more, this would actually respond faster. the time delay would decrease and the rise time would decrease. We'll take a look at this a little bit later in the chapter. And again, this is called input overdrive. And this is happening because as you apply more voltage here, you're basically putting more voltage across the base collector diodes, and it just forces things to charge and discharge faster. So we get to see the speed of the transistor in this case. Our next parameter is input overdrive, but this time from high to low. So if you started out with a high voltage, the output in the comparator would be high. And then when you went below 0 volts, the output would eventually go to the negative power supply, or roughly 0 volts. In this case, I overshot by 20 millivolts. In other words, more negative than 0 by 20 millivolts. And that caused a time delay to occur, and eventually a fall time. If you go more negative than 20, the time delay will shorten and the fall time will shorten. This is because we're applying more voltages to the base collector diodes that cause more currents to flow and to discharge the capacitance of those particular diodes, and so it'll switch faster. You may notice here that these numbers are actually smaller than the ones on the previous page, and so because we have PNP and NPN transistors, the switching times won't be the same. NPNs switch faster than the PNPs because their basic carrier is an electron versus a hole. In the data sheet, they don't talk about the time delay and the rise and fall time much, but what's called a response time. This is the time it takes to go for the output to reach half of its maximum swing. So in this particular case, the half value would be right about over here. So if this was, say, 10 volts and 0, this would be 5 volts. But this response time is really made up of a time delay, which is the time it takes to drop 10%, and then half of the fall time. And the fall time is going from 90% to 10% of the. So it's a combination of things we would talk about with digital circuits of time delays and rise and fall time. But in any case, the response time is dominated by the delay time. If we're going to spice testing, let's take a look at the data sheet again and take a look at those response times when we go from low to high and high to low. So here on the bottom of page 4 is the data going from low to high and then going from high to low. And you can see again there's different response times depending on whether we're going in one direction or the other. And again, this is due to the internal transistors being NPN or PNPs. Now let's test our model and see if some of the things we've been talking about show up in the model. And so let's first take a look at a transfer curve, same file we had for an op-amp, but now we'll put the LM139 comparator, and we'll do a 5 volt, 0 volt power supply. So doing the transfer curve we did in our previous chapter for op-amps, we can also again measure some of the parameters, because at DC, in both cases, whether it's an op-amp or a comparator, we just have an open loop curve and a response. So here the slope of the transfer curve is going to be the open loop gain. It's about 204,000, which is 106 dB, which roughly agrees with the data sheet. We're saturating positive at the 5 volt power supply, and at negative we're saturating about 176 millivolts, and again our data sheet's saying it's about 250, so it's a pretty good model. This would correspond again to our VSAT positive and VSAT negative, as we have a 5 volt power supply and a 0 volt power supply. Now the input offset voltage is specified in the data sheet to be measured when the output voltage is 1.4 volts. In this case it occurs at about 33.942 microvolts. Now in the data sheet it's somewhere around 1 millivolt for the input offset, just like the 741 op-amp. But again, the people that did the modeling at Microsim idealized the op-amps and comparators and basically gave our offset parameters idealized values. We can change this in the modeling by adding a little DC voltage source. I ran the simulation again between 500 millivolts and minus 500 millivolts and took a look at the current that's coming into the comparator, just like we did for the op-amp. And you can see here that Q2 in this case, when the input's negative, is cut off, and that this one is probably in the active region. And the current that's coming in is in the nanoamp range. We'll pick up the number in just a second. And then likewise over here on the other side, when the input goes positive, Q1 gets cut off and Q2 goes active. Go back to the titer of these two in the next picture, so to the previous simulation. And then we could take a measurement of the input offset currents and input biasing currents and they're measured at where the input offset's measured, so at the 33.942 microvolts. So at that value of input, the value of the currents in I sub B plus and I sub B minus I've recorded here. So I sub B plus is a minus 24.971 nanoamps. The reason it's negative is because we have a PNP transistor on the input stage. And for I sub B minus terminal, that was the negative terminal base current, it's roughly minus 25.004 nanoamps. So we take the average of it, you get about a minus 25 nanoamps. And so that's exactly what's in the data sheet. The disappointing part here is that the difference of these two is 33 picoamps, which is basically zero. In the data sheet, it gives a value. We'll take a look at that in just a second. And so again, they've set these input offset values essentially to idealized values of 0. Let's look at the data sheet again on page 2. We get our table. So here's the input offset voltage. For the LM139, it's listed as 2 millivolts, although for a 139A, it's 1 millivolt, which would be the same number as the 741. But in our SPICE model, we have an input offset of 33.942 microvolts. So again, this is a range between plus and minus 2 millivolts, and you could be at 0 millivolts, you could be at 33 microvolts, but probably you're more closer to this number, either plus or minus. The input biasing current is listed as 25 nanoamps. We found it to be minus roughly 25 nanoamps. They don't put a sign typically here, you have to look at the transistor, but the reason it's negative is because we have a PNP transistor on the input transistor. But here the input offset current is listed as 3 nanoamps, and we found that it was 33 picoamps. So again, way off, and again, this is a range, go between plus and minus 3 nanoamps, and it could be 33 picoamps, but probably it's closer to these values. So you gotta be aware of the fact that that's not modeled. You can add a current source in and compensate for this if you need to. But that's something that some models have built in, but these particular models by Microsim don't. And again, by testing these things, you can see whether the model has the parameter you're interested in or not. Let's go back to the testing. Let's run the open loop curve like we did for the 741 op amp. Put the input biasing voltage here, so we're biased on that linear curve. We're not biased at the clipping voltages. So I'll put the 33.942 microvolts here with the same polarity we showed for the 741 and run the open loop curve. And you get kind of a surprising result here. We get a one-pole response. The low frequency gains around 106 dB, which is around 200,000, which is what we would expect, the datasheet's saying. But there's just one pole here. And the 45 degree point is at about 2.17 kilohertz. So the phase angle here never exceeds in magnitude 90 degrees. So this comparator is actually a stable op amp. And so if you put feedback around it, negative feedback, it would become a stable circuit. The real LM139 doesn't do that. In fact, the number of poles that you would see here would be roughly twice the number of transistors, because each base emitter and base collector diode has a capacitance, and those will create a pole for each one of those. So in any application where we put feedback around this to make it like an op amp, this will give an answer that the actual comparator won't. And we'll take a look at this in an example later in the chapter. Next, let's test for the input overdrive. Let's do it from low to high in the first case. So what I'm going to do is I'm going to apply a voltage on my input here and go from a minus 100 millivolts to something beyond 0 volts. Here are 5 millivolts, 20 millivolts, and 100 millivolts of overshoot beyond 0. I left a space between these files, but when I ran it, you take the space out so you can concatenate those and just run one large file, and you can plot everything on one set of graphs if you want to. So here's the results. The reason I picked the 5 millivolts, 20, and 100 is that's what's in the data sheet. And was on with a pull-up resistor here of 5.1K. So here's my input going from slightly negative, but again, not more than one diode drop negative, overshooting by 5 millivolts, 20 millivolts, and 100 millivolts. Now for the 5 millivolt of overdrive, here's what happens. There's a time delay and eventually a rise time, and it's on the order of 1.16 microseconds, and eventually after 1.5 microseconds reaches the 5 volts. Now if you overshoot 0 by 20 millivolts, that gets dramatically cut down. That my delay is about 611 nanoseconds, and then eventually come back up here. And then if you do 100 millivolts, it switches much faster. Now, if you go beyond 100 millivolts positive, you can, as long as you stay below 5 volts, but not much else happens. This is about as fast as it's going to go. We're basically hitting those base collector diodes as hard as we can, and it won't switch any faster. This model is very, very good for this. This is probably the best model I've ever seen for modeling input overdrive. Other models approximate this, but this model has some issues, but this one is where it does a pretty nice job. Let's take a look at the overdrive going the other way. Here we're going to go from a positive voltage to a slightly negative voltage, 5 millivolts, then minus 20 millivolts, and then minus 100 millivolts. And you can see the response on the bottom. So here we're starting out, dropping down a little bit below 0, more and more. So here's the result. We switch with the 5 millivolts of overdrive, and it takes about 763 nanoseconds before something starts to happen, and eventually 1.1 microseconds. If you were to shoot a little bit more beyond 0, switches faster and switches faster, but again, it kind of stops here. It doesn't get much faster than this. But again, you'll notice that these times are much shorter than the previous ones, again, because of the internal transistors. Again, very good modeling for input overdrive effects. And so any application that uses that, this will be a pretty good predictor of the results. I next want to take a look at the output current sink that we talked about earlier. Let's take a look at the data sheet and show what this is supposed to be doing. This is on page 4 on the upper corner. It's kind of an odd looking plot, but this is actually the collector emitter voltage of that output transistor versus the collector current. Now it's not on a log scale, so it looks a little bit goofy, but again, when you're operating over here, if this wasn't a log scale, it'd just be a straight line like this, and then we would just go active. So this 25-degree C line in the center here, if you kind of follow it, is just what we would see like we're looking at 302, or the first page of this chapter. So we can see here that we go somewhere around 16 milliamps, which says that the transistor goes active at that point. Now let's see if the model does the same thing. Now to recreate these conditions, I put a voltage source here. I'm going to vary the voltage, and I put a current here to limit the current. I'm going to plot the voltage here versus the current, but force this transistor to be in saturation. I can do that by putting a negative voltage on the input. That causes that transistor Q to saturate. Let's take a look at the plot now of the voltage at the output versus the current that's going into the comparator, or that output transistor. And you can see the curve on a log scale for current versus voltage looks somewhat similar, although here it's not so great. But again, those are very small values. But when you get to this point of 16 milliamps, the transistor should go active, and you should go like that. The transistor can't go active. The model is set up so that it can't. And that's horrible. That's not a very good modeling technique. It will not sink current correctly if you go active. In fact, that transistor can never go active. It's going to pump more current through one of its controlled sources. So any application that uses this is going to have problems. It will not predict the right answer. Does that mean the model's bad? Not really. It just means that that application, you have to be aware of the model can't predict the right answer. It'll predict some answer, but that's not going to be what you're going to see in lab. Let's take a look at an application. Let's go back and look at our oscillator that we did earlier in the course, and let's change the capacitor from 75 picofarads to 7.5 picofarads. That should make it 10 times higher in frequency. So we would expect about 870 kilohertz from the example we did previously with the model. Let's see what happens. So I plotted the output voltage here, plotted the voltage across the capacitor. It has a little longer initial cycle, then discharges, charges, and discharges. And then I plotted the voltage across the input terminals of the comparator, because when this crosses 0 volts, that's when it's supposed to switch. So initially we start out, the capacitor begins to charge, output goes high, stays high, and the voltage across the input terminals eventually crosses 0, but the voltage at the output doesn't change instantaneously. It takes some time for it to respond. There's a time delay, and then there's a fall time. Eventually, the output transistor changes state, and now the capacitor begins to discharge as it becomes saturated. And again, we begin to discharge, and the voltage across the terminals crosses 0, but we continue to discharge because the transistor is still saturated, not cut off, because the output it's going to take some time delay once we cross 0, and then some rise time. And so that modeling that we have with the input overdrive and the rise and fall times and response times are showing that we're going to get an oscillation around 540 kilohertz, and that is quite different than what we'd expect from our previous calculation or simulation, where by changing the capacitor, we expect the frequency to be 10 times faster. But because of the non-ideal effects of the comparator, it slows down. I don't remember if I actually built this circuit. I'm pretty sure I did, and the results were pretty close to this, but I honestly don't remember. But most of the circuits in the notes I've built and tested, I just can't remember whether I actually did this one or not, but I'm pretty sure that's exactly what you'd see in lab. And so this is some of the testing of the LM139 compared to its data sheet.